Hello everyone. In this lab, we are going to learn about 2D meshing in ANSYS Workbench, and we are going to solve a simple problem related to the beam and see how different types of mesh affects the final result. So these are the details that you will be learning during this lab. These are the details that we are going to discuss in this lab. So the first thing is what is meshing? So I define meshing as a process of dividing complex geometries into small fundamental units from which a similar geometry can be approximated. For example, we have this 2D box, and I can ask you how we can create 2D box from small units. So you can say that we can have similar 2D rectangles or maybe squares using which we can create this whole box. So here we are going to use, so here we have used one element which is called the chord element, and it has four different nodes here. Another method of creating the box is to use the triangular elements like this, and each of the triangular element has three nodes. Or we can use a combination of both the chord element and triangular elements. So it depends on the complexity of the geometry. Sometimes it is not possible to approximate the geometry using only the chord elements. So for that, we may need to switch to the triangular elements and vice versa. So in this lab, we are going to discuss the details related to triangular elements of linear order and quadratic order, and same is the case for chord elements with linear order and higher order or quadratic order. So ANSYS Workbench, it provides us with only two different kinds of meshes that are triangular and chord when we are solving a 2D problem. So there are few properties that we need to look at. There are a lot of them, but I'm going to discuss only two here. The first one is the aspect ratio, and it tells us uh, about the ratio of the largest side of the element that we are using to the smallest side. And for better results, this ratio should be as close as possible to 1. Here you can see the aspect ratio is 1. Here aspect ratio is 2 for the chord element, and same is the case for these triangular elements. So all of these, they have different aspect ratio. So for better results, it's advisable to use aspect ratio as close as possible to 1, but most of the time it is not possible to keep it 1. So we trade off uh, different properties of the mesh that we have. The second quantity is the skewness, and it tells us about the shape of the cell or the element that we are using and how close this shape is to the equilateral triangle actually. So this skewness, it should be less than 0.95. Here we have two different cells. You see the first one, its skewness is almost 0. Here it has more skewness actually. So these are the two properties that we will be discussing and analyzing while solving our problems. So what is the problem under consideration? So this is a simple problem of a balcony. Here you see that this is the balcony, and it is made of a concrete and a cantilevered beam, so kind of a composite structure. But what we are going to do is we will only consider the beam here so that we can analyze the results. The problem is if the deflection in the beam, the cantilever beam, it exceeds 1 millimeter, the concrete that is attached to it, it will start to crack. So we need to reduce the deflection of the beam under the given loading condition to like less than 1 millimeter. So it has to be less than 1 millimeter for beam to be safe. So we will analyze this beam. What are the loading conditions here? So the beam is assumed as a cantilevered member simply, and it has a square cross section for now, and the uh, force is acting on the edge of the balcony, and the force amount is 5 Newton per millimeter. Since the width is like 10 millimeters, we can say that 50 Newton force will act at the centroid of the beam. So if we solve, we need to check whether this beam is safe or not using analytical results and also using the answers. So if we look at the literature, we see that it's very easy for cantilever beams to find the maximum deflection, which is given by the formula shown here, PL cubed divided by 3EI. We have the material properties, and we can simply plug in these values to calculate the maximum deflection of the beam, which is about zero point 0.1 millimeter, and this deflection will occur at the end, like at 100 millimeter from the fixed support actually. So we can say that yes, the beam is safe using the analytical results. Let's see if the ANSYS gives us the same result under different mesh elements. So here, this is the table that we are going to fill. So first we will be using the triangular elements to model the beam, and then we are going to increase the number of elements and see the effect on deformation. We will see what is the skewness, what is the aspect ratio, and deformation. So we will create similar graph for the chord element as well. So let's shift to the answers. Uh, this problem is also a 2D type problem which can be solved using the plane stress case. And you can see the width of the beam that is installed in the balcony is 10 millimeter, which is very less than the length. So we can simply model it as a 2D plane stress element. And the material is structural steel, which is by default the material that is used in the engineering database. So I'll go to the engineering database to check the material and its properties. So structural steel is there and the properties are here. We have all the properties. So closing engineering data, the first thing that I need to do is to change the analysis type to 2D from the properties, and then I'll open the design modular for modeling the section of the beam. It can be modeled simply in the XY plane. Here we can sketch a simple rectangle. First of all, changing the units to millimeter, and I'm going to select a rectangle here. Now this rectangle, we can dimension it. So the length is 100 millimeters and the height of the beam is actually 10 millimeters. So I'll simply convert this simple sketch into surface. So here we have the geometry. Um, Now the question is, can we use any symmetry condition in this particular case to further reduce the problem? So the answer is no, actually, because if we apply the symmetry condition along this central line, the neutral axis, actually, you see that the although the beam shape is symmetric across about this neutral axis, and also the fixed boundary condition is same, but the force is only applied on one side of the beam, so we cannot apply any symmetric boundary condition here to further reduce the problem. However, it can also be solved using a 3D line element, so that we will discuss later in the course. Okay, here we have the geometry. Now moving on to the next step of the analysis, which is setting up the mesh and material and boundary conditions for solving the problem. So here we have the geometry. We are solving the plane stress case, and material is structure steel. The next step is to create the mesh. So if you look at the mesh closely, I'll show you some controls here. Here you see that the first option is related to the physical preference. So it tells us which kind of solver are we going to use for this particular problem. Since we are solving the structural analysis and we want to find the stresses and strains, so mechanical is the type of the physics solver that we are going to use. And there are other solvers like CFD, explicit, electromagnetics, and etc. The second portion is relevance. It tells you about the fineness of the mesh at global scale. So if you shift the relevance to 100, the mesh will be fine. If you shift it back to minus 100, it will be very coarse. And at moderate level, this is like zero. The next thing is the order of the element. This shows that the elements that we are going to use, whether the triangular elements or the chord elements, whether we want them to be linear or quadratic, and we can set this to program control as well. The next option here is the size function. Here you will have multiple options like adaptive, proximity and curvature, curvature, proximity, and uniform. So these are the multiple options that are available. If we look at the curvature-based options, they use the algorithm that takes into consideration the angle of the curvature while creating the mesh, and also the minimum and maximum size that we specify. Similarly, proximity, when we are modeling different bodies for the meshing here, so the proximity controls considers the meshing based on the bodies that are near to that particular mesh. Similarly, we have adaptive control and uniform control here. So you can learn about the details of these size functions. They may be different in higher versions of the software in their guide, and you can play around with those as well. So what I'm going to do is to use the uniform control, and here we can specify the minimum size of the element that we use and the maximum size of the face that we use. And then there is this growth rate. The growth rate tells us about how the mesh element grows as we move layer by layer from one side of the model to the other side. So I'll just generate this mesh for now. And you see by default, the ANSYS is creating this mesh, which if I go to statistics, consists of 75 elements with 282 nodes actually. So uh, the if we want to have more control over the mesh, we can click on the mesh, right click on the mesh, and we can select the method and sizing, refinement, and face meshing and other details here. So first of all, I'm going to look at the method of the mesh that are available. So when I select this whole body, so there are multiple selection filters. You will see that I'm getting this option which is quadrilateral dominant method. So chord dominant method, it will force the solver to use majority of the elements in this domain that are chord shape, or we can uh, use a combination of chord slash triangle, or we can enforce all chord settings as well. So if I change this and generate the mesh, so previously all the elements they were already chords, so you will not see much of a difference. But if I'll change this to uh, here triangles and then generate the mesh, here you will see that now all the elements that are here created for this beam, they are of triangular type. So what we can do is we can further refine the mesh using the other control method. So I'll start with the triangular method, and I'll select the sizing here. When we select the size, we can size the mesh elements based on the corners, or based on faces, or based on the bodies. So these are the different options that you can select. Uh, so what I'm going to do is I will select the corner here, and this corner and this corner, and instead of specifying the size, I'm going to use the number of divisions. So I only want one triangular mesh element along this direction. The size function that I'm going to use is uniform, and we can change the behavior or growth rate from these edges as well. Let me create the mesh and see what happens. There is no change in mesh uh, for the controls that we have inserted. The reason is that the global controls, they always have higher priority over the local controls. And if I look at the maximum face size here that we set up, the maximum face size is 3.95 millimeter, and the width of this beam is about 10 millimeters. So we have selected one element, one division along this. So if ANSYS try to make only one element along the width, it will not work because of these global settings. So I'll change this global setting to 10 millimeters so that I have one element along the uh, width as well, along the width of the beam. So when I regenerate this mesh, you will see that I have now one element along this width. In total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 elements. Here we have 20 elements, and they in total they have 63 nodes. The next thing what that I'm going to do is to further reduce the number of mesh elements. I'm going to insert the sizing and select this edge as well, and I want only one element across along this side as well. When I'll generate this, you will see that the similar issue occurs. We are not updating the mesh because of the global control. So I'll change the maximum face size to 100 millimeter, and regenerate the mesh. Let me change the behavior to hard. Okay, so these are different settings that we can use in order to achieve the desired results. So behavior hard means that the algorithm will try to enforce the settings that we have selected here. And now we only have two triangular elements. So in total, we have two elements, and these two elements they share nine nodes actually. So why are there nine nodes here? You can see that. So one node is here, the second one is here, and the third one is here, fourth one is here. There is no point in having nine nodes for this. But yeah, we set the element order to program control, and it is possible that ANSYS is on by default since the number of elements are very small. So there are only two elements. It is converting the behavior to quadratic. Let me change this to linear, and now we are explicitly defining that the triangular elements that we are using, they are of linear order. And here we have four nodes which are at the corner. So you have seen that in case of the element order quadratic, it will be nine nodes. So why are there nine nodes? Four nodes at the corner and one node here in this at this portion, one node here in this portion, one node here in this portion, one node here, and one in the middle. So these are the additional five nodes that we have. So in total, we for quadratic elements we will be having nine elements, nine nodes for calculation. So I'll just shift this again to linear, and now if you want to look at the quality of the mesh, here you can see different mesh metrics that are available. So the first one is the aspect ratio, and here you can see that we have the aspect ratio of 10.85, which is very high. And we mentioned that in order to have a good mesh, the aspect ratio needs to be near to 1. The second metric that we can have a look at is the skewness, and the skewness is 0.88 actually here. So you see we have these different properties. You can click here and see which elements have those properties. So this way you can have a look at the uh, skewness of different elements, and other metric which is the element quality. You can look at the quality and orthogonal quality of the element as well. So these are the few features that we look while creating the mesh. The next step is to insert the fixed support. So this beam is fixed from the left side, and there is a force which is acting at this corner. So I'm going to select the point here because I'm solving the problem in 2D, and there is a force of minus 50 Newton in negative Z direction. So we can solve this. Let me insert the directional deformation, and we want to find directional deformation in y-axis now. So let's have a look and reevaluate the results. Here are the results, and the deflection in this case is 0.0129, which is very far from the original results that we have. Let me check if everything is all right. Oh yes, so the thickness of the beam is 10 millimeters. So we specified it to be 1 millimeter, and I'm going to solve it again for the required thickness, and let's look at the directional deformation. Now this is much smaller actually, but this was the result that I was expecting with two elements. So I'm going to keep a note of this here. Let's see. Uh, what I can do is note down the number of elements, number of nodes, and then maybe aspect ratio. Let's see. And finally, the deflection. So these are the four parameters that we will be looking at while solving the problem. So the first thing is we have four nodes, and the aspect ratio is here, which is 10.775, and with this the deflection goes to 0.00129114, which is a huge difference from uh, from the actual result. So what I'm going to do is increase the number of elements here from 1 to, let's say, 10, and remesh. After remeshing, we are going to run the solution again. And here we have a result which is minus 0.023 now. So how many elements do I have? So I have 22 elements to 20 elements now. 20 elements with 22 nodes, and the aspect ratio is 1.559, and the deflection is 0.023 minus 0.0231 millimeters. Let's change the sizing one more time, and now in the other direction, let's say. So if I change it to maybe uh, 5 elements here and change the behavior to hard, let's see if it works. Okay, so it is not working in this case. I was expecting this. So I'm going to delete this edge sizing here, and will insert the sizing on the face and set the face size to, let's say, 2 millimeters. Now, when I generate the mesh, you will see that there are a lot of triangular elements, and uh, we have each element with 2 millimeter thickness, or 2 millimeter size. And now, if I solve this problem with lot of these triangular elements, you will see that we are approaching the exact solution, which is about 0.09 millimeter. So this is 0.09 millimeter. So the exact solution was 0.01 millimeter. But here in this case, we have 552 elements with 327 nodes, and the aspect ratio is about 1.19. So this is about 1 aspect ratio, and you see that how the results are converging to the original results that we have. So one last time, what I can do is I'm going to uh, remove this sizing again. Let's see what happens with higher order elements. And we can insert the edge sizing as we have done previously to number of divisions 1, and another edge sizing with number of divisions 1. Change this to hard and regenerate the mesh. So there is one thing that I'm going to change here, and that is the order. So if I change the order here, you will see the difference in the results. Let's solve this. So what happens with the higher order is, if I note down all of these parameters here, with higher order we have two elements but with 9 nodes, and the aspect ratio is also 10.75. And if I look at the deflection, you see that the deflection with only two elements, with higher order elements, is quite near to the exact value that we wanted. So if I change this further, let's change this to 10, as we have done uh, this for the previous case. Regenerate the mesh, solve this. So after solving, we get almost 0.0998 as the deflection. So with just 20 elements, we have 63 nodes. Aspect ratio is 1.559, but the solution for deflection, it's like uh, 0.09. Yes, so this is 0.0998. So this is approximately zero point 0.1 millimeter, which we were targeting. So you see that by using higher order element, we can have more nodes, which will require more calculations. The solution will be slower, but it could be accurate in terms of deflection. But we need to check whether the same relation will hold for the values of stress or not. So that you need to check after looking at the stress values in the solution. And it could be different for the stress. So the next portion is to change the elements here from triangles to chords. So I'll just change this to all chord, and then change the edge sizing from 1. And here we can have only one element with 4 nodes. I can generate the mesh. So this is a one quadrilateral element, one node, one element with 8 nodes. So I'll change its order to linear first. So this is the linear order element. So it will have 4 nodes. Yes, one element, 4 nodes, and I can note it down here. So we have got a one with 4 nodes. Aspect ratio here is 10, and let's see what is the value of the deflection. So reflection here is 0.0756 with one element only. And if I change the elements to let's say 10, so I'm changing it quite drastically, so it has to be changed slowly so that we can see the effects. With 10 elements, 22 nodes. So with 10 elements, we have 22 nodes. The aspect ratio is exactly 1, and the solution is, you see, minus 0.10042 millimeters, which is much more closer to the exact results that we have. Okay, so let's use the higher order chord elements now, and I'm going to change this to 1 again, uh, from linear to quadratic element, and solve it. So with this solution, you will see we have we will have for chord elements 8 nodes. Aspect ratio in this case will also be 10, and the solution is much more accurate. So if I change this to 10 now, let's solve this directly. So it will first mesh it and then solve it. Okay, we have the direction deformation, which is 0.09994, which is almost of the same accuracy as this one. So it's like up to three decimal places if you look at the answer. So these are the general trends. You can see that in general, the chord elements, they are much more accurate if we compare the linear chord element with linear triangular elements. Chord elements are much more, they give much more accurate results. And if we compare the order, if we compare the solution based on the order within same type of elements, higher order elements, they give better results. So this is the general trend that we observe, and you can see that the aspect ratio, with change in aspect ratio, how the reflection is changing. So the trend for the stress could be different. So this is all for this lab. Now you can move on with filling up the table for the triangular elements and 2D elements, chord elements here. You can change the aspect ratios and note down the stresses as well and see what are the effects, create the plots and see the results. And finally, if you look at the book that we are following, you need to solve the section 3.2 with different mesh settings that we have, and then submit it in today's lab. Thank you so much. We will back with the